Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome back. Today we are going to talk about sampling and non-intrusive testing for subsurface exploration. But before we get into the topic of discussion of today's presentation, we are going to look back to the question set of the previous lesson. The first question that I asked was what are the methods of intrusive subsurface investigation. Basically, in the discussion of this particular course, we just talked about two basic procedures. One is excavation of a pit or a trench in the ground for exploration of shallow layers underground, and the second thing that we discussed, second group of procedures that we discussed are based on drilling a circular hole in the ground and conducting some sampling exercise. We did not talk about sampling in the previous lesson. We are going to talk about the details of those procedures today, but basically we talked about two different procedures for subsurface investigation. One is excavation of trenches or test pits, and the other one is drilling and sampling. Now, the second question that I asked was why it is imperative to maintain an exhaustive field record during subsurface investigation, and I asked you to explain with examples. Now, the major problem that the designer faces is to get a clear picture of the layers that are there underground, and for this he or she needs to have an idea about what is the sequence of drilling, what kind of problems were encountered during drilling, and so on and so forth. And some of these issues I already have discussed in the previous lesson, and for example, we can talk about the coloration of a particular rock or soil sample, and these colors typically change as the rock or soil sample they get exposed to the weather. Now, another thing that you could think about is, in some cases, because of exposure to weathering and because of the unloading, because of the loss of confinement after sampling, some types of rock and soil samples, they are notorious in changing their strength and structural characteristics. As an example, we can think about the rock type called shale, claystone in a sense. These rocks basically, if they are kept exposed to the nature, then they actually ravel, and the cracks develop, several sets of cracks develop at a very close spacing within the mass of the rock, and if they are not identified or tested within a short period of time after sampling, they actually disintegrate almost completely in some situations and become like powder. So, in these situations it is extremely important actually for the field investigator or the field inspector to describe the strength and other behavioral characteristics of the sample, so that the strength taken in the design of a facility that is going to be constructed on top of these layers or these geologic units, they are not underestimated or overestimated. Okay, then the third question that was given was for you to explain the significance of the following of a few field descriptions. The the say for example the description that was given was gravelly sand with silt, some clay. Now as soon as that description is seen by a user of the drill log, then what he or she has in mind is that this particular sample contains a very large proportion of gravel and sand, and it also has got some percentage of silt and some percentage of clay. Now the qualifiers that are used here, with this qualifier and some, these two qualifiers, we know what these qualifiers mean in the terminology of identification of hand samples obtained during a drilling operation. Now with, as we have noted, with means that that particular component, silt in this case, has got it has got a percentage of approximately 20 to 30, and some, the type of constituent that is qualified with qualifier some, that has got a percentage, I mean it has got a percentage of about 12 to 20 within the total soil mass. So this particular soil has got almost a majority of gravel and sand. It is composed of majority for the main part by gravels and sands, gravel size particles and sand size particle, and it has got 20 to 30% of silt and 12 to 20% of clay. So this essentially is a deposit which has got a very wide range of grain sizes within its volume, and this type of deposit, one such deposit we talked about in one of the previous lessons is till deposit. Till deposit, that is directly deposited from ice, glacial ice. So that is in a sense the second part of the third question, and what I asked is a possible name, possible geologic name of such a deposit, and this deposit could indeed be a till deposit. Okay, so that takes care of the question set, and now we move on to the subject matter of today's lesson. So what we are going to try to do today is to describe a few common procedures for extracting soil samples and rock samples during what is common during subsurface exploration or drilling and sampling procedures that we discussed to some extent in the previous two lessons, and then we are going to list the relative advantages and limitations of these procedures, and we are also going to be able to describe a few common procedures for non-intrusive methods for subsurface exploration, and we should be able to also describe the limitations and advantages of these procedures. So that those are the objectives of this lesson, and in the first part of this lesson we are going to talk about soil sampling, and then we are going to move on to rock sampling, and finally we are going to get into non-intrusive testing procedures. Now soil samples are extracted basically more usually they are extracted by inserting a sampling device into the soil or excavating out a volume of soil, and we talked about some of these procedures of obtaining samples by excavating out a block in the previous lessons, and also depending on what procedure is used during the sampling could be disturbed or it could be undisturbed. So we are going to look at some of these procedures that give you disturbed samples and some of the procedures used for obtaining undisturbed soil samples. Okay. First of all, we look at disturbed soil samples. Now, what you mean by disturbance, that is the first question that comes into mind. Now, by disturbance what we mean is that the distribution of individual soil grains or the distribution of the void spaces, the pattern of distribution of the void space within a general volume of soil that gets changed during the sampling procedure. So, that is disturbance, and disturbance could be caused by the procedure of insertion of the sampler into the ground, and it could also be caused because of the unloading that takes place during the drilling procedure itself, or the lack of the confinement which vanishes as a result of the drilling procedure, that itself is going to cause an unloading, and that will translate into disturbance. Then the third part of disturbance could be caused because of the circulation of the drilling slurry that is done normally in some of the drilling procedures that we have already discussed. Then the second thing that you have to keep in mind is that most of the sampling procedures will cause disturbance to the will introduce disturbance to the sample to some extent. Now, what is the purpose of obtaining disturbed soil samples? The purpose of obtaining disturbed soil samples is for visual identification of the sample in the field as well as in the laboratory later on, and we could also use the samples obtained in this procedure to reconstitute a sample in the laboratory for further testing. And examples of disturbed soil samples include auger sample or samples extracted using a thick walled sampler. We are going to look at these procedures in the next little bit. Okay. Now, here on the left there is a picture that shows a disturbed soil sample obtained by inserting a thick walled sampler. In this case the sampler is a split spoon sampler. We are going to talk about split spoon sampler later on, the details of construction of this type of sampler later on. So, this one is a split spoon sample. What you have got here, so this one here is the sampler, this one and this one, and this one here is the soil sample, and you can probably make, if you can make out, if you look carefully, this particular sample is a sample containing it is a sand sample basically, and it has got some gravel also in it. You should notice the presence of drilling slurry near this particular portion of the sample. So, the nature, the disturbed nature of this particular sample is evident from the pattern that you see on the picture there. Okay, so that is a split spoon sample. It is a disturbed sample. It is taken by a split spoon sampler, and it has got a lot of disturbance inserted because of the fact that this particular sample is obtained using a very thick walled inserting a thick walled sample into the soil, and secondly because of the intermixing of the soil with the drilling slurry. Okay, so that is the details of a split spoon sample, and then the picture on your right shows an auger sample. So, in this case you saw a picture of an auger in the a few in one of the previous lessons, and here what we got actually is an auger which is being used for drilling. So, this is our auger, and this auger is bringing out the soil from underground on the auger flights. So, this disturbed sample is called an auger sample. So, here the disturbance is even more in comparison with a split spoon sample, in the sense that we do not exactly know from which depth the auger sample is actually coming exactly, and they are totally altered in the interlayering within the different portion that might be existing in underground structures. They are totally destroyed as the sample is brought to the ground surface by the screw action of these augers. So, these samples are also retained for very approximate identification, could be retained actually for very approximate identification of the samples and finding out their relative distribution of grain sizes and so on and so forth. In comparison, the thick walled samplers, the amount of disturbance introduced by thick walled sampler is relatively less, in the sense that in many of the thick walled samplers you could actually see the fine interbedding that is present within the soil layers, and those interbeddings are not identifiable in case of auger samples. So, these are basically two of the two examples of disturbed samples of varying degree, introducing a varying degree of disturbance to the sample. Okay. So, then we move on to the undisturbed soil samples. In this case, the distribution pattern of particles and void space is retained. Unlike disturbed soil samples, in undisturbed soil samples we have to lock in the pattern of distribution of individual soil particles and void spaces within a certain volume, within the sampled volume. Now, obviously undisturbed soil samples, extraction of undisturbed soil samples is a more expensive proposition in comparison with that used for those used for disturbed soil sampling. Now, these undisturbed soil samples are used for specialized laboratory tests, and these tests are those that are particularly affected by sample disturbance. Examples of undisturbed soil samples include block samples for cohesive soils and frozen samples of cohesionless soils. How to extract frozen samples? Actually, in order to extract undisturbed samples of loose cohesionless soils, it is essential actually it is almost essential to freeze a certain volume of soil underground, and using the procedure of rock coring that we are going to discuss in the next little bit, to obtain a core of the frozen soil. So, that is the procedure used for extraction of undisturbed soil sample of cohesionless soils. Now, undisturbed soil samples also require very careful handling after the samples are extracted and brought to the ground surface, until they are taken to the laboratory and they are set up on a test stand and tested. So, between sampling and testing, the sample handling has to be carried out in a very careful manner, so that disturbance is not introduced into the sample during the transportation of the samples. Now, in between the disturbed and undisturbed soil samples, we also can talk about an intermediate stage, and that is high quality soil sample. So, in this case, this disturbance introduced into the soil sample is relatively less, is much less in fact, in comparison with those imparted by procedures that we discussed for obtaining disturbed soil samples. Now, these procedures are much more economical in comparison with the procedures that are followed for obtaining, for extracting undisturbed soil samples. Typically, they are much more economical in comparison with the procedures for obtaining undisturbed soil samples, and these soil samples are also extracted for laboratory tests, provided that the test is targeted in obtaining a soil property that is not affected much by the sample disturbance introduced during the sampling procedure. And also these particular type of sampling, they involve, there are two different procedures that we discuss, two different examples that we consider here for obtaining undisturbed soil samples, and they are by using large diameter samplers and thin walled samplers. They also require careful handling and testing. Now, why large diameter and thin walled samplers are used for obtaining high quality samples, that become evident when I draw this particular sketch. Let us say we try to introduce a thick walled sampler, cylindrical thick walled sampler into the ground. We are going to look at the definition of a thick walled sampler in the next little bit. Now, let us say we are introducing a thick walled sampler like that. Thick walled sampler. What is meant by thick walled sampler actually is that the proportion of the wall thickness, so this one is the wall thickness, is quite large in comparison with the sample diameter. So, let us imagine that we are inserting a thick walled sampler into the ground, and let's for convenience, let's imagine that the ground, the soil underneath the ground surface is a varved deposit. I am just giving you an example here. So, if you recall, a varved deposit has got laminations of two different types of soils like that, and in this case typically it is alternate layering of clays and silts. So, let us say the deposit is like that, and in this case these are all the silt layers, and the ones in between are clay layers. So, they are thin laminations, really a few millimeter thick. So, now when the sampler is inserted, you can see within the sample the laminations, they are curved down like this, because of the friction that develops between the interface of the sampler and the soil inside it. So, you are going to have the laminations bent like this, and that is an indication of the sample disturbance. Now, you can see that near the center of the sample, the sample is relatively undisturbed. Sample is relatively undisturbed. That is one thing you can see. And the other thing that is important is that this amount of distortion of the laminations inside the samples taken within the by the thick wall sampler, the amount of distortion or the amount of bending, that is greatly minimized if the wall thickness of the sampler becomes smaller and smaller. So, that is the reason why if we could devise a sampler which is of relatively large diameter and the wall thickness is relatively small, and if we can introduce some ways of reducing the friction inside the sampler, then we are going to improve the sample quality by a great extent. So, that is the reason why thin walled and large diameter samplers are used routinely to obtain high quality samples. Okay. Now, as I mentioned also earlier, that these samples also require careful handling until they are tested in the laboratory. Okay. So, soil samplers, we need to look at typical soil samplers then. So, these soil samplers are typically pushed into the soil layer, or they are hammered into the soil layer. Now, as I indicated in the previous sketch, that the disturbance introduced into the sample because of the insertion of the soil sampler is reduced by decreasing the wall thickness. It can also be decreased, the disturbance can also be decreased by sharpening the shoe, and also by having an inner and outer clearance and a piston. So, what is meant by that? Let us look at it in a little bit more detail. So, what we want to have is a sampler which has a small wall thickness in comparison with the diameter of the sample that is taken in. So, this is the sampler that we are talking about, and in this case you can realize that the wall thickness is a very small proportion of the diameter of the sample. Then the end of the sampler is crimped in this case, and what this crimping does is that when the soil enters into the sample, so this is the soil entering the sampler, soil entering the sampler. So, what happens actually, there is a gap, there is a very small minute gap in between the soil that is entering the sampler and the sampler wall, and this gap actually minimizes the friction, sample to soil friction, and that itself minimizes sample disturbance. So, that is how disturbance is minimized, by having a thin walled sampler and also by having a little bit of inner clearance. Then the second thing that is important is to have a piston is to have a piston on top of the sampler on top of the soil sample, and this particular piston prevents the soil from outside the cross section of the sampler to get in to the sample, get inside of the sampler during the insertion process, and that actually minimizes the disturbance more. So, this is a piston that precludes, that actually prevents the soil from outside of the sampler cross section to get within the sampler during the insertion process of the sampler, and that in turn minimizes the disturbance. So, disturbance is minimized by this particular disturbance is minimized by having a piston as well. Okay. So, what are the measures then? We have to have a thin walled sampler, we have to have a relatively large diameter in comparison, relatively large diameter in comparison with the wall thickness of the sampler. We need to have an inner clearance, a little bit a minute inner clearance, so that the friction between the soil inserting soil getting into the sampler and the sampler wall is minimized, and we want to have a piston inside the sampler which actually prevents soils from outside the sample, outside the cross sectional area, outside the outer diameter of the sampler to get into the sampler, and these all measures actually minimize the disturbance imparted into the soil sample. Now, what is a thick walled sampler and what is a thin walled sampler? Now, thick walled sampler are those samplers which has got an area ratio of greater than or equal to 10%, whereas thin walled sampler has got an area ratio of less than 10%. Now, what is an area ratio? Area ratio is the ratio of the area underneath the wall of the sampler to the cross sectional area of the soil sample that has been taken within the sampler during the sampling process. So, let me explain what I mean by that. Let us say, let us look at a cross section of a sampler. The sampler looks like this, and this is the cross section of the tube, sampling tube. So, in case there is no, so this is the thickness of the sampler wall, this is the wall thickness, and then inside of it is the soil sample. Let us for simplicity consider that there is no inner clearance. So, let us assume that the diameter of the soil sample is d, and let us assume that the wall thickness in this case is t. So, the area which is shown by cross hatching, that area is going to be pi times d plus t square divided by d plus 2t square divided by 4 minus pi d square divided by 4. So, that is the area, of the cross section of the tube itself, and this we divide by the sample cross section, and then what we get is the area ratio. So, this is the definition of area ratio of a sampler. Now, as we have seen, that area ratio, what we want actually in order to minimize sample disturbance, we want to have an area ratio of less than or equal to 10% or less than 10%. Okay. So, this particular sketch actually shows two different samplers used for soil sampling, and the one on the top is a picture of a thick walled sampler. So, this one is a thick walled sampler, and the sampler in this case is a split spoon sampler, which is the same sampler which was shown in one of the pictures earlier. In this case what we have is a shoe. So, this one here is the shoe, and this one is the split spoon. This has actually, this particular part has got two different, it is composed of two different segments. So, if we take a section there, then it is going to look like this. So, it is composed of two hemispherical segments. This is the cross section that I am trying to draw. And then you can see that the bottom end, so this one enters the soil first, this end enters the soil first, and this is the top end. So, this is the top of the sampler and this is the bottom of the sampler to the right, and what is there at the bottom end, the shoe has got a threading, and these two hemispherical halves of the split spoon, they actually screw on to the shoe and they are tightened, and once the shoe is a single piece construction, and once the shoe goes on to the bottom end of the split spoon of the two hemispherical portions of the split spoon, then the split spoon behaves in a they cannot separate from each other. Then at the top end of the sampler also there is a threaded portion, and this is the thread. This one you can see a threaded portion near the top end through which the split spoons are attached to an adapter, and this adapter itself has got another set of threads. So, these threads that I am talking about in this case, these threads, they screw on to the drilling rods such as AW rods or BW rods, and also is of interest in this case that there is a ball. You can see that there is a ball inside of the sampler. By the way, this particular view is a cut view of the sampler. So, the top half of this picture shows the outer appearance of the sampler, and the bottom half of the sampler actually gives you a cut section. So, you can see the ball there near the top, and this ball allows the air and water to escape as the sampler is inserted into the ground. So, that is basically the construction of a thick walled split spoon sampler, and once this sampler is taken out of the ground, it comes out of the ground with the soil sample inside, then the shoe and the top adapter is unscrewed, and then the two halves of the split spoon can be disassembled, and this disassembled configuration was shown in the picture that was shown before. Okay, so, that is the construction of a thick walled split spoon sampler. This sampler we are going to look at again when we talk about a testing procedure called standard penetration test later on. And then the bottom sketch shows a thin walled sampler, and in this case the sampler is a it does not have a piston in it. So, this particular sampler is called a Shelby tube. So, what is there actually, like in the top sketch there, this particular picture also shows a partially cut view. So, the upper half of this picture actually it shows the outer appearance of this sampler, and the bottom part shows the cut view or the section of the sampler. So, here obviously this is your wall thickness, whereas in the thick walled sampler you can see that that was the wall thickness. So, it is obvious that the wall thickness is quite small here. Actually, both these sketches are drawn to the same scale approximately. So, you can see that relative to the diameter of the sample itself, the wall thickness is quite small in case of a thick walled Shelby tube sampler, and here the adapter near the top is shown on the left just like before, and this is the shoe that cuts into the soil as the sampler is inserted into the ground. So, in this case the sampler is not hammered in, but it is simply pushed into the soil gently. So, Shelby tube is a pushed in type of sampler, whereas the split spoon thick walled sampler is typically hammered into the soil. So, that is the construction essentially of a thick walled and a thin walled sampler. Okay. So, now we try to look at a little bit of piston sampling. So, in this case what is shown here is the schematics of a piston sampling procedure, and this type of sampler is called a stationary piston sampler. So, the sketch on your left actually shows the piston sampler placed at the bottom of the borehole. So, this one here is placed at the bottom of the borehole. So, this one is the bottom of the borehole, bottom of a pre-drilled borehole. And then what happens, the piston is kept stationary. You can see that on the sketch to the right, piston is kept stationary, and what is done is to insert the thin walled sampler into the soil underneath. So, this is the thin walled sampler that we are talking about. At the end of the stroke, this has gone into the ground, into the soil underneath, and the piston, which was originally at this particular location, it remains at the same elevation. So, this is the location of the piston after the sampler has been inserted, and you can compare it with the original elevation of the piston. Both these sketches are constructed at the same vertical elevation, and they show the section of the sampler basically. So, that is how a piston sampler, stationary piston sampler operates, and because the piston is at the bottom of the borehole, when the sampler enters the soil, it actually prevents the soil from getting into the sampler by the when the sampler tries to displace the soil. So, that is the reason why piston samplers are used in order to obtain soil samples with minimal disturbance. Okay. Now, we get into rock sampling. So, here the samples are extracted by drilling through rock layers drilling through rock layers using a core drill. We have seen in the previous lessons and examples of core drill bit. Now, disturbance in this case is minimized by introducing double or triple tube core drilling. Core samples are described and identified in the field. They are saved in core boxes before taking to the laboratory for further testing. Now, we look at the core drilling procedures in the sketches shown here. So, one on the left actually is showing you a double tube core drilling. So, in this case what is happening, the sampler, so this is the rock core insert getting into the tube. So, this one is the core and this is the drill bit, and you can see here that the drilling slurry, this is the slurry in, and the yellow arrow there shows the slurry out. So, by introducing an inner tube, we are not allowing the slurry that is getting out, flushed upward, this particular slurry to come in direct contact with the core that is taken within the sampling tube. And because of the fact that there is no direct contact between the slurry and the sample that is getting into the tube, the sampling disturbance is going to be minimized, it is hoped. Then you could also have a triple tube sampling, and that is shown on the sketch to the right. Here you can see that this one is the first tube, then you have got the second tube, and finally you have got an inner tube which is also called the liner. So, here you have got a double protection, double protection in between the core that is getting into the tube and the slurry that is being circulated. And one of the drill bits that is used in core drilling, an example of it is shown on the picture on the right of this particular slide. And in this case the drill bit is a diamond drill bit. So, these tips, the tips here, they are diamond tips. You could also instead have a tungsten carbide tips in relatively softer layers, softer rocks. Okay, this is an example of a core sample of a basalt. You can see that the discontinuities and joints, they are clearly visible on the sample itself. We are going to talk about later how to describe the discontinuities and the joint sets within such core samples, and this core sample is ready for transportation to the laboratory. Now, we get into non-intrusive methods. Non-intrusive methods involve no intrusion into the formation. So, this particular technique is useful if exploration has to be carried out underneath an existing structure, or the site is underlain by a number of underground utilities, or exploration requires to penetrate contaminated sites which should not come into contact of the devices that are going to be otherwise inserted into the formation, because then those devices will have to be cleaned up properly, and that could be in some situations very expensive. So, these procedures include seismic velocity profiling, resistivity sounding, and ground penetrating radar profiling. We look at now the details of these things. So, seismic velocity profiling use seismic body waves, and the body waves are in a sense P waves or S waves. So, P waves are similar to the sound waves in a sense. In this case, the particle motion is in the same direction as the propagation direction. S waves, on the other hand, the particle motion is in a plane in a direction transverse to the direction of propagation. Now, seismic waves, both these body waves during propagation, they follow Snell's law. That means the sine of the incident angle divided by the sine of the reflected angle, or refracted angle rather. They are the ratio is equal to the ratio of the velocity of the propagation of the waves in these two medium. So, that is actually indicated on the sketch to the right. So, here we have got an interlayer, the top above the interlayer the velocity of propagation of seismic wave is V1 and at the bottom it is V2. So, in that case sin I over sin R will be equal to V1 over V2 as seen on the equation there. Now, this is the seismic velocity profiling is usually based on reflection of seismic waves, and the reflected wave in this case this is the reflected wave is the one that is shown there, and the wave below is the refracted wave. This is known to you from preliminary physics courses. So, basically we make use of reflected waves and refracted waves. How do we do that is going to be explained in the next little bit. So, here what we have got a very heavy beam, say. So, we have got a heavy beam and we hit this particular beam, first say to the right, and then we hit this beam from the left. Now, because of the disturbance caused by this particular thing, seismic waves they are going to start propagating, and in this case we have got a layered structure. So, this beam is at the surface of the earth, and what we do, we place a series of detectors of seismic waves. So, these are the detectors, this one, and this one, as well as this one. So, these detectors they pick up the signals as they reflect from the interlayer boundary and come back, and also they refract and travel along the interlayer boundary and come back. And because of that we can get different arrival times. So, from those arrival times, the pattern of those arrival times, we can construct the layered structure underneath the location which is being surveyed by seismic velocity profiling. So, here the waves that arrive in sequences are shown on the sketch on the plot to the right, bottom right of this particular slide. So, in this case this one is the direct arrival, that means the waves that originate there and travel along the surface and arrive at a given detector. This one here is refracted wave. So, that go down and start traveling along the interface of layer 1 and layer 2 and arrive at detectors. Then you have got reflected waves, their arrival is showing as shown in that particular plot. So, using these patterns actually you can construct the velocity structure. You can find out what is the velocity of V1, what is the thickness of V1. So, what is the thickness H1, and also you could get velocity of V2 and so on and so forth. That in essence is the seismic velocity profiling. Then resistivity sounding, it attempts to detect resistivity contrast of different layers. All different types of geologic mediums has got different resistivity values. For instance, clays exhibit typically low resistivity, whereas granular soils, coarse grained soils, they have got larger resistivity values. Then the governing equation in this case is shown there, is shown below. So, that is essentially rho is equal to 2 pi times d times E over I. So, rho is the resistivity in this case, d is the d is the distance between the electrodes that are used in order to circulate the current, and these electrodes are placed at the ground surface. Okay, E is the drop, E is the voltage drop between the detectors, and I is the current generated at the detectors. So, in this case typically what is done is, on the ground surface you place two electrodes, let us call them E1 and E2, and then you have got detectors. So, let us call that D1 and D2. So, in here basically this is the D, this is the value of D in the equation, and this is driven by a battery, actually by a voltage supplied across the electrodes, and then you are going to measure the voltage drop and the current in between the detectors. So, those things are used in the equation on the left there. Now, depth of detection in this case is approximately equal to the electrode spacing in this case. So, basically the depth of sampling of different layers is going to be equal to d in this case. Okay, GPR profiling, which is, this is also very similar to the seismic velocity profiling, but in this case typically we make use of reflection only, not refraction. So, in this case what we have got a source of radar waves S1, and then we have got a detector called R1. So, this is what we do. Basically we use a source and we use a detector to find out what is the radar signature of the subsurface layers, and in a sense, and then we alter the location. We take the source to a different location and we take the detector to a different location, and by looking at the signature for different detection signals detected, we construct the the profile of the subsurface layers. And in this case what we have got an arrival from which arrives directly from source to receiver through air, then we have got direct arrival, but this is from soil through the surface of the soil, and then we also have got reflected signal arrival, in this case arrival of reflection, and that is shown by that line there. And by looking at the patterns, these patterns, we also just like before we can find out what is the interlayer structure. Okay, here we make use of radar waves between 200 to 900 megahertz, and we use reflection signature as we have indicated. Then the antennas are shielded to eliminate reflection from above ground objects, and typically the depth sampled is less than or equal to 10 meter. The resolution is not very great in this case, and it does not work well for many absorbing material, absorbing soil types such as clays. To summarize this particular lesson, what we learned here are different types of procedures for drilling and sampling. We looked at a few common procedures for non-intrusive methods of subsurface exploration, and then we looked at the list of relative advantages and limitations of these procedures. We end with a question set. The first question is, what is a thin walled sampler? Then how sampling disturbance to soil and rock samples is minimized? What are the advantages and limitations of GPR profiling? and what are the advantages and disadvantages of seismic refraction profiling. Try to find out the answers to these questions at your leisure, and we are going to be when we meet again, we are going to talk about the answers. Thank you very much.